people were interested in, but it's time to start. Do you have a question? No, you're just listening, huh? Anybody else have specific questions? I mean, if you have other questions, but we probably ought to talk about structural materials a little bit. Okay. So have people decided on? You're taking what is TQM, you said. Okay. What are you, have you decided on a module yet? You don't have to decide on your, okay. What about yourself?
I watched one on like definition.
Oh, okay. That's an old one. I only did that one once. That was actually the second term as a sophomore. I taught that course, and then 30 years later I taught it. But I had more examples by the time I taught it the next time. I actually liked that one for other reasons. But anyway, yes. Okay. Okay, fine. Okay. So does anybody, those of you it's hard to watch some, do you have any specific questions? I didn't expect you to have a whole lot of questions this first week. You're busy figuring out what's going on. So I prepared something. I didn't prepare it. It's something I've done in previous years. And I thought at least for structural materials, rather than talking about Harvard and MIT and things like that, we could talk about factors of safety. You're a mechanical engineer. How many of the rest of you are mechanical engineers? Okay, so I got 3 out of 5 of you here are mechanical engineers. So what do you understand a factor of safety to be?
The amount that you'll build or tolerate something to, so that it can, the maximum, so factor of safety is like, you have the maximum threshold that you'll operate at, and then however many extra factors it can theoretically go to until it breaks.
Right.
That's your factor of safety.
Right, okay, so it's capacity or capability of strength. I mean, if we're talking strength of materials. So Dr. Belmar, being more of a mechanical engineer, he calls it the capacity and then divided by operating stress. So if the capacity is a stress, how much does it take to break it, okay, or fail it? You got to remember, in some cases, failure is not breaking something. A lot of times we think of breaking something in two as the failure stress, but you could have failure if something starts to deform, which means it would be the yield stress. And the operating stress is often defined by a code or standard. And we're going to go through, I'll talk a little bit about that. And stop me if you have questions on some of this. It's supposed to be a recitation, right? But the capacity is the capability to support a stress, and the operating stress is what you would calculate from mechanics as your nominal stress, and it's often defined by some code or standard that's been around for a while. The oldest factor of safety that I've seen was some books go through and talk about bridges, a couple of books on history of engineering written by civil engineers. And remember, civil engineering, if you watch this thing, I talk about the history of engineering, and the first engineering school was West Point in the United States, and it was military engineering. And the next engineering school I've learned since then, it's not Rensselaer, it's actually Norwich in Vermont, had an engineering program in 1820, and RPI wasn't until 1823. But RPI is obviously a more well-known engineering school than Norwich now. Norwich is still a small school. It's a good school, but it's smaller. Anyway, so it wasn't until the 1820s, and they both came along with something they called civil engineering to distinguish it from military engineering. Okay, originally engineering was military, building breastworks and dams and bridges for catapults and things like that. And then with the Erie Canal, Norwich and Rensselaer being near upstate New York, started producing students who could help build the Erie Canal. And so civil engineering was really the only main type of engineering. It was really sort of MIT in the 1860s that started breaking things up. Number one at MIT, course one, is civil engineering, okay? But the bridge designers, and I did find some references about 1850, And they had a factor of safety because they were just beginning to be able to calculate the strength of a beam. If you go back, Galileo has a picture of a weight hanging off a beam. And he was doing experiments, kind of Galileo's way of doing things, to understand the strength of a beam. Okay? Well, they started developing those equations in the mid-1800s. And so they could calculate, kind of like a sophomore in mechanical engineering, okay? They could calculate the strength of a bridge, and they found a factor of safety around 6, okay? About that time they actually had a commission in 1850 in Britain that determined they should have a factor of safety of 6. Because before that, it was all sort of, well, I built one like this and it didn't fall down for the last 50 years, so I'll build one similar to it. And then someone would come along with a different material or a different design to try to save some money or some time or something, and the factor of safety would go down and things would get worse and worse. And history has a way of repeating itself. You've all seen the Tacoma Narrows Bridge failure. Okay, I'm getting nods from most of you. So the Tacoma Narrows Bridge failure in 1942 was an example of their making things too slender. And the winds came down the Tacoma Narrows, and this thing, they called it Galloping Gertie. I saw it in my freshman physics class here at MIT, and they were teaching waves. Okay, and you see the waves on this bridge. And then about 10 years ago, the American Society of Mechanical Engineers came up with the granddaddy code, the boiler and pressure vessel code. So if you have a whole set, takes up about this much shelf space and costs $15,000 every 3 years. You get all the updates for 3 years, but the boiler and pressure vessel code was actually, they got together and I used to have a picture, I probably ought to go dig it out again. But it was a shoe factory down here in Brockton, Massachusetts. The boiler blew up, kapow, in around 1905 or something like that. And the ASME decided we're getting tired of this. Turns out the first research contract ever let by the U.S. government was in 1836 or something. Some steamboat on the Ohio River blew up, and Congress actually appropriated some money for someone to go and figure out why these boilers were blowing up and killing people, okay? So pressurized boilers, you know the Barlow formula, sigma is P R over T, right? Pressure radius divided by the thickness. Those types of equations were around, and the boiler and pressure vessel code is the world code today. There are some countries that don't use it. Mainland China doesn't use it because they don't want to spend $16,000 to purchase a code. They basically have their own codes, and they sort of copy what's in the boiler and pressure vessel code, and they don't care about copyrights and things like that. But you can't make a boiler or pressure vessel out of gray cast iron because gray cast iron has lousy fracture toughness. You can make it out of ductile iron, which is almost like steel, but even so, ductile iron being a casting can have larger flaws, and they require, even today in the code, a safety factor of 5. Whereas typically for steel, and there are different safety factors, the code this thick will have different requirements for different nozzles and connections and things, but generally for steel it's about a factor of 2 is the safety factor. And then you can say, well, is that based on yield or is that based on tensile? Well, it's sort of based on tensile, but if we're talking A36 steel of 36 KSI yield, it turns out about 18 or 19. And they got a table, and it depends on the specific steel. There's lots of experience over the years. But it's basically 55 or 60% of tensile, which gives you a factor of 2 of safety. If you go through this, the operating stress is 55 or 60% of tensile. When you get to higher strength steels, things change a little bit. But in general, a safety factor of 2 is good for steels. Why? Those of you who are mechanical engineers. What do you know about fatigue of steels? Do you know anything about fatigue of steels? and why they would choose a safety factor of 2. If you look at the old-fashioned SN curve, where you look at stress versus number of cycles, you'll find for steel it comes down and it tends to level out, and we sometimes call it the fatigue limit. Is at 45 to 50% of the, typically it's the yield stress, okay? That just, now, aluminum doesn't have a fatigue limit. Aluminum kind of keeps on going down like that, and they've gone out to 10 to the 8th cycles. You start figuring at 1 cycle a second on a fatigue machine, that's a year-long test. And they've gone 10 to the 100th. Well, they didn't do a 100-year-long test. They start going at higher frequencies in their testing. You start going at 100 hertz, you have machines that can do it, but it turns out you have to start worrying about heating of the sample. You're putting enough work in the material, it'll heat up on you. So you have to be careful when you start going to such long tests. Usually, we're talking way out here at 10 to the 8th. Usually these plots only go out to 10 to the 7th. This little break is usually somewhere around 10 to the 3rd, 10 to the 4th, 10 to the 5th. So where that curvature is in there. So 10,000 cycles or so, we go from what we call low cycle fatigue to high cycle fatigue. You have a factor 2 safety and you're good, okay? You shouldn't have a fatigue problem unless you have stress concentrations and other things, okay? So that's why we have safety factors of 2 for steel in the boiler and pressure vessel code. They have all kinds of things to take care of stress concentrations in the design. You have reinforcements around nozzles and stuff. I've seen failures in pressure vessels. Well, first of all, the boiler and pressure vessel code, virtually all of these codes in the very beginning, they'll have a scope. The first paragraph will be scope of this code. And it will tell, actually the first paragraph might be the first 3 pages in the boiler and pressure vessel code. It doesn't apply if you're less than 100 psi and 1.5 cubic feet. I think that's right. And then, or 15 psi and 1,000 cubic feet. Basically, it's pressure times volume. How much energy did you store in this pressure vessel? If it doesn't have much energy, we don't care, is basically what ASME. The explosion won't be that big, okay? If it's got a lot of pressure or a lot of volume, and I can't remember what the 2 numbers are right now. There's a couple of different ones. But basically, they're just saying with a certain amount of energy, you're going to have a big enough bomb that you don't want to be there if it goes off. The American Welding Society Structural Welding Code has a static and a dynamic. Static for buildings is 5/3. World Trade Center was 5/3. Okay, I gave you an article I wrote, and I used that 5/3. I knew that principle. It's in the code, and that building would have been built to the AWS Structural Welding Code. These are the 2 major structural welding codes in the world, okay? Almost everybody except the Chinese and a few third world countries don't use the ASME code, even though it's a US code, because it's sometimes called the granddaddy of all codes. The AWS Structural Welding Code, it kind of is a companion to it, but it's basically has something for bridges, something for bridges, dynamic, and something for buildings, static. Bridges, of course, are dynamic with trucks going over them and things like that. Dynamic, why 2? Because you got fatigue. Buildings, it's not really fatigue in buildings, okay? Not at the high level of stress. So those things sort of make sense. Then, OSHA for ladders and scaffolding, if it's man-rated, which means I got a cherry picker and someone's going to be up there in the basket, factor of 4. Someone could die. If it's in OSHA, if it's more than 6 feet off the ground, you got to follow the code. Because if you start figuring out the energy of a fall, you can break your back from a 6-foot fall. you won't break your back from a 2-foot fall. Okay, there's not enough energy to break, unless you've had other problems health-wise ahead of time. So, man-rated equipment, ladders, scaffolding, these lifts, everything will be 4.0. Just an extra factor of 2 for a little extra safety. It's still the same steel. Tree stands doesn't come under the boiler and pressure vessel code. It's not a pressure vessel. Doesn't come under they have their own tree stand manufacturers association. And that's only in the last 15 years or so. But people are dying or being maimed by tree stands falling out of the tree with the people on them all the time. Okay. Oh, you're not a hunter, obviously. Neither am I. But if you were in Pennsylvania or Colorado or certain places where the deer run wild, anyway, they run wild all the time. But they'll go to the store and they'll buy this little tree stand. And there's lots of mom and pop shops. Some guy is a hunter and he says, I got a better design. And he doesn't know anything about design. And he starts making it and selling it at Cabela's or Bass Pro Shops or something. And you carry this thing in. You don't want it to be too heavy, usually made out of aluminum. And you climb the tree and you wrap this thing up there and you sit up there and wait for Bambi to come by so you can go blast Bambi, right? Or if you're a really good hunter, you use a bow and arrow to slice right through Bambi's heart, right? Does that explain it? Okay. Some of them have canopies. I mean, some of these things get very elaborate. But it's something, if you don't have anything else to do with your life, you go out there and wait for Bambi to come by in the fall. The thing is, if you're down at regular level, they'll smell you. I mean, the animals will smell you. And the deers know when hunting season comes, right? And so they're more skittish, actually more skittish in the fall anyway. But people will sit out there some people go out there 8 hours a day sitting in the cold, waiting for their buck to come by, and they count the number of points on the horns of the antlers and stuff. The X33 space plane was supposed to replace the space shuttle. They designed it for a 2.0, had some bonding problems, and I must talk about it. I know I talk about it in some of my lectures, I don't remember which ones. But they had some problems, and so it was a $1.3 billion program. These vessels that held the liquid hydrogen tanks were about the size of a house. And actually, I could have brought in the composite material. I have a piece of it. Very, very lightweight. Size of a house, and the basic structure weighed about 12,000 pounds. Very few houses are that lightweight. But this had to go in space. They had some problems with some of the bonding of the carbon fiber and the Nomex honeycomb with the adhesive, and so they didn't want to cancel the program. It was a rush program in the early 90s to demonstrate rapid prototyping, and so they just recalculated their safety factor and found out they had a 5% safety factor. Good enough. So they put it in test in Alabama. The only place you can get 50,000 gallons of liquid hydrogen is Huntsville, Alabama, where they're testing rockets and things. So they put it in test, and everything was fine until they started to warm it back up, and they were giving everybody high fives because they had passed the test, and they were going to use this and put it in a prototype and go from Edwards Air Force Base to Dugway Proving Grounds in Utah, and get up above 100 miles. So they actually got to space and prove out the design. But then they saw a pop. And all the frost on this thing is on the video because no one's going to be near this. This is a bomb, okay? 50,000 gallons or whatever it was. I have to go back and check, but it's the size of a 2-story house. It split open. Nothing exploded, but then they went back and they found they didn't really have their 5% safety factor. I mean, this thing was a disaster from the initial fabrication, and they're just hoping they could get this thing to pass so they could keep their $1.3 billion program going. NASA canceled the program. 1880, the New Orleans levees had a safety factor of 1.3. One of the civil engineers designing those in 1880 was my grandfather. So there. Grandpa, you needed a bigger safety factor. However, back then, they were lucky if they could even calculate the safety factors, but they did. So there's something on safety factors to give you some idea of the different ranges. A safety factor, it's hard to decide what you want to call your capacity. Your operating stress will be defined historically by the codes and standards. And then it's really a question of what risk are you willing to take, okay? And if it's man-rated, you want a bigger safety factor. I used to think, until I started working on them, that I'd never want to get in a helicopter. Those things are just, as they sometimes call them, flying fatigue machines, right? But as I got in and I started doing some helicopter failures, it turns out helicopters tend to have a safety factor of about 10 on most parts. And believe it or not, they're weight critical, but they have had enough failures over the years that they do a lot of work. And if you get in and actually look at the designs and calculate safety factors, you find helicopters have tremendous safety factors, which is why most helicopter accidents are pilot error, okay? And we could go through some of that. Okay, so that was one thing. Like, we could talk about safety factors. So just a couple of slides that I put together some time ago. Anybody have any questions? I could go through some other things. What types of things are you interested in? I might as well, there's only a few of you, I might as well try to do some things that you might be interested in. So I gotta find my cursor. Where'd my cursor go? Well, I have something on bolting here too, but oh, here's my cursor down here. Bolting. Okay. Anybody have any questions? No questions? Okay, so I served on a committee about a year and a half, 2 years ago, that was commissioned by a department, part of the Department of the Interior, called BC, Bureau of Safety, Environment and Engineering or something. But BC is basically the part of the Department of Interior that regulates things like offshore structures in the Gulf of Mexico. They were the ones, their predecessor, they changed their name after what's the Horizons? The BP Horizons failure in the Gulf, you know, the big oil well blowout. They had a different name before that, trying to hide afterwards. Okay. But we've had 3 other near misses in the last, since 2000. Okay. And they're all public knowledge. They're not hiding anything. It's just they didn't end up with big oil losses like the BP disaster. And so a number of the other failures had to do with bolting. And so we just finished this report. Does anybody know what the National Academies and the National Research Council is? You probably don't know about these things, right? So in 1863, Abraham Lincoln chartered the National Academy of Sciences. And it's not a government agency, but it has a charter from the president to advise the government, or governments primarily, it can be state governments as well, on matters of science and technology. And it's for years, it was sort of an old boys club. They're now trying to get more women and minorities than they are slowly. But when I say old boys club, in 1966, the National Academies of Engineering, or the National Academies of Sciences, was being politicked that they should have something separate for engineers. And so they formed the National Academy of Engineering, 16 people, of which 2 or 3 were MIT professors, one from this department. Was it Phil De Bruyne? I think it's Phil De Bruyne. But anyway. And they ended up electing, you can only be nominated by people who are already members, nominated and supported by people who are already members. So when I say it's an old boys club, started out with 16 men, and for years it was almost all men. Now it's about 15% female and like 1% or 2% minority. But anyway, the average age of election is about 69, okay? But it's considered the highest honor that an engineer can have. There's about 2,000 members of the National Academy of Sciences. There's about 2,000 members of the National Academy of Engineering. And a few years after the National Academy of Engineering, around 1970 or so, they started what's called the Institute of Medicine. And there's about, it used to be only about 1,500 or 1,200 doctors. I think it's around 2,000, mostly MDs or PhD researchers. And so you've got about 6,000 people who advise the government on different matters of science and technology. Well, they formed in around 1910 or so the National Research Council. And this National Academies building is right on the mall near the Lincoln Memorial. Okay, just a couple of blocks down from the White House. It's not a government agency. Sometimes they call it a quasi-governmental body. It's not owned by the government. It's a private institution. It works very hard to have objective studies. When they have a study, it'll list in there, there's 15 or 16 or so of us on this committee. And there might have been about a third of them might be members of the National Academy, who are these elected old boys. And then the other people will be put on because of their expertise. And well, we're all put on because of our expertise. But other people who are not as old and senior will be put on that have particular expertise. So I've served on a number of these. I served on it for the Army Ballistics Lab down in Aberdeen Proving Ground, Maryland. I've served on one for the Alvin submarine. Could we afford to build a new Alvin submarine and stuff? Anyway, so I served on this one about bolting technology in a marine environment. And here, the risk, there's actually a book from Harvard School of Public Health. Risk is equal to the hazard times the consequences. Now, this is not unique with that book from Harvard, but risk and benefits of hamburgers and cheeseburgers. Okay. It's the probability of an event times the severity or consequences of the event. And there are actually standards out on this stuff now, many of them starting with the military, who have had some pretty major disasters at times, but they're designed to have disasters. Bolting, you can have bolts in tension or shear, typically. They can get more complex, obviously. And they're all over bridges and buildings. It turns out, if you look at some books on bolting, this is typical fractures at 4 shear tension ratios. This is a ratio of 100% shear, when you just, slicing it like a bologna, right? And this is one time shear, and what's this, square root of 2 over 3? No, square root of 3 over 3, I think is an important parameter out of mechanics, okay, ratio. And it still looks like that. If you get to tension is square root of 3 over 3, and then the shear is square root of 3 over 3, and then the tension is 1, you start seeing a shear, or a 45-degree shear plane, and then you get a pure tensile load. So the type of failure in a ductile joint can vary depending on the shear tensile ratio. It turns out for undersea drilling, bolting is getting more and more important. The first undersea platforms, in a sense, were off the coast of Bakersfield, California in like 1908. And they were just going from the land, and they hit the ocean, and they started moving out to where it was like 10 or 20 feet deep, and it wasn't very deep. But then they kept on getting deeper and deeper, and they have designs for up to 10,000 feet deep now. The Macondo well, or the BP Horizon well was, can't remember. I think it was a floating production or a tension lake platform. I don't remember. But all kinds of complex things. These things now can cost $5 billion for the production platform. Okay? They're big, big things. They have blowout preventers. That's what failed in the BP system. This is a person, or that's not a person, well, that's a fence. That could be the height of a person, but these can be 4 or 5 stories tall. Great big valves in here that are going to shut off the flow if all goes well. And that will be down the bottom of the ocean, maybe in 10,000 feet of water. 1, 2, 3, 4, 5, 6 valves in this thing. Okay? Different types of valves, shear rams that was one of the things that failed on the BP Transparent, not Transparent Horizon, that's Transparent Horizon is a sculptor over by next house, or whatever the dorm is over here. But in any case, BP Horizons, one of the shear rams had a problem where basically if all else fails, they just have big shears that are supposed to squeeze this thing off and cut it in two and seal it. Okay? Just big hydraulic rams. You can analyze bolts in terms of springs, a spring model. The bolt is a spring, and then you have compression between your two things that fairly small spring force here can generate significant spring force here. You have lots of stress concentrations in bolts, okay? Tensile stress, and here's a higher stress down here near the threads and the nuts. Stress goes up because of the reduced section because of the threads, and then other things. There are all kinds of high-strength bolts. Some of these critical structures have bolting things that you wouldn't even recognize as a bolt, okay? But it turns out one of the problems with bolting is most people, anybody ever used a torque wrench on a bolt? Okay? What do you think the accuracy of that is? Pretty bad, plus or minus 30% in some cases. But that's what people use when they're trying to be precise in the strength of the bolt. To get good fatigue strength in the bolt, you want the bolt to be tensioned to 70% to 90% of its yield strength in order to get good fatigue resistance. And you got plus or minus 30% as your ability to do it. So in really critical applications, such as where I first saw it, on the crankshaft of an airplane engine, they actually grind the tip of the bolt and the bottom of the bolt to an exact dimension, and someone takes a micrometer, and this thing is 2.62 inches before they tension it, and after it's 2.68 inches. And so it's stretched 0.6 of an inch. And the stretch, Young's modulus, is pretty well known, and you can get down to plus or minus 10% of your stress in your bolt, which is what you really need. And so they sometimes have holes down the center of bolts where you can actually put a little gauge, okay, if you have longer bolts. For those little, small little piston engines for the prop aircraft, I mean, you just need a 3-inch micrometer, but that's what people use. There's a guy who's a graduate, actually I think he may have passed away now, John Bickford, a graduate of mechanical engineering at MIT, wrote a book this bolting. Anyway, it's got a long title but it's about 1,200 pages long. And John Bickford knew more about bolting than anybody else in the world. And so when people were putting bolts in a nuclear reactor, you hire John Bickford, okay? Because he knows how to bolt things together properly. Why do you use bolts? Why don't you just weld things? You got to take it apart. Right, exactly. It's harder to take welds apart. You can do it, but it's harder. But anyway, here's something Bickford did for the Nuclear Regulatory Commission. Bolt clamp variation, calibrated torque wrench, plus or minus 17 to 23%. Hard joints, soft joints, which is the compliance of the joint, plus or minus 20 to 40. That's my plus or minus 30, I said. And you can use torque wrenches, impact wrenches, hydraulic tensioner, stretch control. Stretch control is measuring the elongation of the bolt with the micrometer, right? Now they actually use ultrasonics to measure the stretch of the bolt. You can measure the length of the bolt fairly precisely before and after tensioning, so far as that goes. But even stretch control, plus or minus 10 to 20%. Turn of the nut, plus or minus 10 to 20%. Operator feel, plus or minus 100 to 200%. Now, a lot of times, people are using plus or minus 100 to 200%. Okay? And by the way, on the offshore structures, torque wrenches, plus or minus 30%. And they wonder why they have failures when they put these things down in the ocean.
So what's between a torque wrench and a micrometer? For those, like if we were to be out using it, like torque wrench is plus minus 30%.
Right.
On me.
What can you do?
Yeah. How do we get greater accuracy without going?
Well, you actually have to plan for this. I mean, there are some you can use with big bolts. You can use hydraulic tensioners in some cases, and these things basically. It's not just someone feeling it or using a torque wrench, which is sort of crude anyway. The hydraulic tensioner, you're measuring a pressure on a hydraulic cylinder, and so you can get that within 1 or 2%, which gives you, in some cases, plus or minus 10%. But that's when you get a bolt bigger than about 2 or 3 inches, and it's no longer somebody's arm anymore. You got to have a hydraulic system tightening that. And you got some bolts out there that the nuts can be this big around, right? So what's in between? Unless you're in a critical application like the nuclear business or the aerospace business, most people still use torque control. That's why the guys in the oil and gas industry. And we had a 3-day workshop, and they didn't want to do anything other than torque control because it's easy. Okay? You get a number. They're happy with the number. The number is garbage, but they're happy with it because they have a number. They can write it down in a little log and say, we checked it. Still garbage. We've known about ultrasonics and things for decades, 50 years, 70 years, but still people use the same old technology. Anyway, if you go through Bickford's book, a lot of the stuff came out of Bickford. Cut threads versus rolled threads. So if you have a smaller bolt, you can machine it and cut it. But most bolts nowadays, up to a couple of inches in size, they actually cold roll the threads. They have some hard dies that the dies are at sort of an angle, and you roll this and you make a thread by crushing things. And so at the bottom of the V, you have compressive residual stresses. Gives you much better fatigue resistance. So you like rolled threads, for example. One of the big things on the torque wrench, one of the big problems is lube control, okay? If you're lubricated, you'll get the same normal distribution, but if it's lubricated, the torque will be much less than if it's not lubricated and you got dry friction, right? And there's your plus or minus 30% right there. So one of the things you can do if all you have is a torque wrench, you lube it.
Are you saying lube the threads?
Yeah, you put grease on it. You'll get a more consistent result. Bickford has some nice little, if you go to his book, he has some nice little bullet points. And one of them is, he has some little some little couplet that goes something about if uniform torque is what you want, lube it or something. It's a little bit better than that, but I don't remember what it is. But basically, lubricated bolts will give you more consistent torque.
Could you maybe create a table that has stuff like materials, coefficients of friction, and
Oh yeah, he's got that in his book.
and all that? So
All this is. If you want to know anything about bolting, just go to Bickford's book, and he's got hundreds of references to the mechanical engineering literature. People have studied this over and over and over. They just don't follow it. I mean, it's not we don't know what to do, okay? But lubrication is a good thing. Torque turn, you torque it and then you do another quarter turn at the end, and that can give you, it's a little variation or some variation like that. That can actually give you some things, but you still get a histogram. There's some critical applications I went through, just some things I had worked on. This was actually a whole lecture once. But they're variable pitch propellers. If you've got you want to have more efficiency in your drive of your ship at different speeds, particularly in some military ship, you actually have your propeller blade can twist depending on the speed that you want to fly, you're rotating. And you have a gearbox in here that changes the pitch of the propeller. Well, these bolts, you lose one of those bolts, you lose the ship, okay? Because now the thing's out of balance, severely out of balance. You're going to bend the shaft, you're dead in the water. And if you're a military ship, that's not good. So here's some of the internal mechanisms of one of these variable pitch propellers, a gearing mechanism in here. These bolts have holes down the middle. You put a long micrometer in there to measure the stretch. You don't torque those, okay? You can do fracture analysis on bolts. I don't know, you happy? You don't have any questions? You can do fracture analysis. This is fatigue. So I look at this, and Tom Eager looks at this and he says, well, I have a fatigue crack that runs this deep. This is the final fracture. This little serrated stuff over here is part of the final fracture. This one, this is the fatigue fracture. That's the final fracture. Turns out metallurgists have been using these types of fatigue analysis diagrams for different types of stress. I blew it up on the next page, but high nominal stress, low nominal stress. High nominal stress, the final fracture area is the dark area. High area, low nominal stress, small area. Different amounts of stress concentration, tension or tension compression. If you've got experience, you can tell a lot about the fracture of a broken bolt. In fact, back 30 years ago, a nuclear reactor had a problem on some of its bolts, and I was working for a test lab, this is the early 80s, and they said, we're going to send you a bolt, and we're not going to tell you anything about it. We want to know what you can tell us about it from just looking at it. So they sent it to us, and I looked at it and said, well, low cycle fatigue, moderate nominal stress, variable amplitude loading, because some of the fatigue cracks were difference in width of how fast it was growing, and it was operating at 600 degrees Fahrenheit, and they were all surprised. Well, you get blue coloring, and the temperature was not uniform with time, okay? You get blue coloring in your steel. It's called, they sometimes call it blue brittleness in carbon steels, but they call it temper colors, and the steel actually forms a blue oxide around 600 degrees Fahrenheit. Go look it up on the internet. So I knew the temperature had to be, in some cases, I could see the different striations and I could see the variability. I could tell the size of the high nominal stress, and I think I told them it didn't have a stress concentration, okay, as well, just by looking at the fracture. Sort of like reading tea leaves, right? Except it's knowledgeable tea leaves. So lots of, okay, so I had a building fall down at a sports complex at a university south of here. And if you look at these fractures, oops, I got the wrong one. I haven't gone far enough. Here are some of the fractures. Fatigue fracture right here, final fracture, high nominal load, ductile all the way, fatigue fracture nearly half of the way before it broke. The reason this thing broke down while they were erecting it was because some of the anchor bolts were broken. Why were they broken? It turns out, actually, it was I don't remember if it was fatigue or if these were heat treating defects. But anyway, then I had another one. This one was on a turntable, and you can see the fatigue crack A, B, and C. Low cycle fatigue, high cycle fatigue, low cycle fatigue, final fracture has a different appearance to the fracture. And then I actually had a quiz for the students after some things. This is one where obviously the nut wasn't tight. It was peening itself apart. I had another one with some really big bolts. This was a 50,000-ton forging press. There's only like half a dozen of these in the world. And the post basically are have bolts, 4 big bolts, about 1 meter across. Okay, so this one, stress concentration, there's the fatigue crack, there's the final fracture. They changed the steel, and they thought they were going to a higher strength steel and everything would be wonderful. Now it turns out the fatigue crack is this big. There's the final fracture area. Yeah, it was higher strength, but it still broke due to fracture mechanics, and we won't get into the fracture mechanics right now. But, okay, lots of things you can tell about things if you get into all the details. I mean, one time they taught you about fatigue. One time they taught you about fracture mechanics. One time they taught you about heat treatment of steels. They all actually fit together. And you want to solve the real problem, you got to know something about all of them. So, okay, next Monday, Dr. Belmar will be here. I'll be in Henderson, Kentucky. And then I'll be here the next Monday after that. So bring your questions or email your questions to me or to Dr. Belmar. Anything you come up with, and we will try to say something intelligent about your questions. This time, I was just making up my own questions.